Okay, hi everybody. Welcome to part 2 of the March 21st video. I'm going to talk a little bit about some of the material in a section of your chapter 15, ranging from page 691 to 695. So I want to spend the first few minutes talking about this graph that appears on 691. It's kind of interesting because it shows 4 different types of temperature dependence for reaction rate constants. A probably looks the most logical to you. Back in Gen Chem, you learned that when you raise the temperature, the reaction is going to go faster. Earlier this term, we talked about collisions and how collisions getting more energy leads to more effective collisions. So this looks like it's the most normal relationship between rate constants and temperature. And a fellow named Arrhenius noticed that as well in the late 1800s. I have a couple of slides later in which he tried to fit this to an equation, and we'll explore that a little bit later on. But there are some unusual cases that are illustrated here. Here you see in B a rate increasing with temperature, reaching a maximum, and then decreasing with further temperature rise. In C, it shows a steady decrease of rate with temperature, and in D, you see what goes on in a chain reaction. You have kind of the normal exponential increase, but then all of a sudden, a reaction literally becomes explosive when it goes just off the charts. So, as I say here in my paragraph, in B and in C, you might expect that those are surprising. Because again, think about what's happening at the molecular level. When you raise the temperature, the molecules move faster, and you would expect that the fraction of collisions that activate the molecules will react more. We find that mechanisms can have a range of complexity, and therein lies the source of some counterintuitive behavior. In an enzyme-catalyzed reaction, that's what's going on in B. The enzyme must often be in a specific conformation to react with a substrate molecule. While the enzyme is in the native state, the reaction does indeed increase with temperature because you're going to have more motion among the reactant molecules, and so more often they'll collide in the correct way. But for an enzyme at a higher temperature, the molecule may undergo denaturation, which essentially, if you're not a biochemist, just means that the molecule is going to change its shape to such an extent that that active site may not even exist anymore, and it's going to lose its effectiveness, therefore decreasing with increasing temperature. The behavior in D corresponds to a chain reaction. Basically, you just get a point at which there's uncontrolled growth in the reaction. We're not going to spend a ton of time on that, but let's explore these exceptions a little bit more on the later slides. So here's an example more of C that is really surprising, that increasing the temperature actually makes the rate go down. Our text says that this is rather rare, but a well-known example involves in the formation of smog, which of course is a gas phase reaction. So the formation of smog is nitrogen dioxide, occurs when nitrogen oxide reacts with oxygen gas. The reason this is really involved with internal combustion engines is that as the fuel is being burned in your engine when you're driving, a little bit of air gets caught in there as well. So since air is 80% nitrogen and those temperatures are kind of high, you can create some nitrogen oxide inside the cylinder of your engine. In the atmosphere, when it collides with oxygen molecules, you can get smog. This shows a second order in NO and first order in N2. As I say here, the mechanism is believed to involve 2 bimolecular steps, and I encourage you to use a piece of scratch paper to figure out how to get from this mechanism to the one in bold. So recall that the rate of a reaction is the rate of the slow step. However, you can't include an intermediate in a rate law, so you have to make a substitution. So notice here that I wrote the first equilibrium step as an I wrote it as an equilibrium constant, or you could separate it into your different rate constants. And so I'm asking you a question here. If you can calculate what's the K observed using the Ks of the individual reactions. So why don't you calculate that when you get a chance. Furthermore, this is interesting. The equilibrium of the first step is exothermic. So remember that exothermic reactions treat heat as a chemical product. So while this first step is in equilibrium, if I raise the temperature using Le Chatelier's principle, that's going to force the reaction backwards. And so if the decrease in equilibrium constant with temperature is a larger effect than the increase in K2 with temperature, then the overall rate will decrease with increasing temperature over a certain range. So basically we see that that's happening here. Notice that for this formation of smog, the rate of formation of smog gets slower with temperature, principally because the reverse step of the reverse reaction in the first step is dominating over any increase you get of the forward of the second step. So that's why you get this kind of rare event. I found this in another Chang textbook that's focused on biochem. I thought it was kind of a neat experiment, relatively simple, to explore the complexity of different kinds of DNA. So don't have to be a biochemist to understand this, but it basically shows this experiment where you take a double strand of DNA and you could break it into short pieces by sonication and heating. Upon cooling, the little pieces of single-strand DNA will recombine, but of course only if it's with a complementary piece. The rate of renaturation, basically the rate of you finding your mate, your match, is second order, first order in each piece, and is relatively fast the less complicated the DNA sequence is. So what we mean here, if you look at this graph, I think it's pretty neat. The graph to the right, this one I just underlined, compares several kinds of DNA strands arranged in terms of complexity. A synthetic piece of DNA with all the same base pairs on each single strand, so poly A and poly U and poly A. So basically they have this. So this is a synthetic piece. And if you're breaking it up into pieces, there's lots of the matches that are floating around in the solution. And so that's going to be relatively quicker than more complicated pieces of DNA. So what did I write here? A synthetic piece of DNA with all the same base pairs on a single strand will recombine very quickly because there are complementary pieces all over the place. However, as the DNA sequence increases in complexity to the extreme of having no repeating sequences, the amount of time it takes for pieces to recombine increases exponentially, reflected in the position on the y-axis, which contains a time component. Actually, I think that's an error. I think it's the x-axis has a time component. If you look carefully, there's a little t in there. The half-life of recombination is reflected in the position of each example at the 0.5 fraction reassociation point. So your complexity, they're saying, of comparing one type to another is where you cross this middle line, kind of a half-life, if you will. So I thought that was interesting. So I had mentioned Arrhenius a little bit earlier, and I know you've seen this equation before. In fact, I noticed that a few of the problems, I think two of the problems I had already assigned, two or three of the problems I had already assigned involved using the Arrhenius equation. I ask you to revisit those, the answer keys already on Sakai, and also do a few more to really get this down. So here's the thing. So I said back in 1889, I call Arrhenius a PChem OG. He was really, really important to a lot of what you've learned this semester. If you recall, especially the distribution of speeds, he was involved, him and Boltzmann were really involved with that. But experimental data, so remember that first curve I showed you before, where you had kind of an exponential growth of rate constants with t? Arrhenius is just fitting this equation. It's empirical. There's no, what should I say? It's just a fitting of the curve. It doesn't come from theory at all. But he's just fitting an exponential to this with a pre-exponential constant or frequency factor that's labeled capital A, and then a familiar term to you, the activation energy. We know, for example, from Gen Chem that that's essentially the height of this curve that you need to go to in order to get to your products. We will see later in the theory part of this chapter that the frequency factor is related to frequency of collisions. So you might remember equations we did earlier like Z1 and Z11. So the frequency factor is related to that. and so therefore it is temperature dependent. However, in a limited temperature range, if you're looking at ranges of about 50 degrees or less, the exponential part of K is way more tied to temperature than the A part. So that will make our math easier. One thing our text points out is that the exponential part is actually, again, reminiscent of something you had seen earlier, where I think I have this. You might remember this equation way back in chapter 2. I think it's 2.33 according to my notes, where you saw an equation like this. That was a equation for figuring out the population of some higher energy state based on the difference in the energy. So you could figure out what fraction of the molecules are in the higher state using this fraction. This is actually related to this equation. Notice the form of the equation is really similar. Basically, why is there a connection there? Because an increase in temperature causes an increase in the kinetic energy of the particles. This leads to more frequent collisions and the reaction rate increases. If I increase the temperature, more of my molecules will enter a higher state over here, and that's going to change this fraction. In the example that we're considering right now regarding reactions, we're talking about the fraction of molecules above this point is going to increase when you increase the temperature. So the area under the curve of the red is bigger than the area under the curve of the blue. Whoops, red is greater than the area under the curve in the blue. And again, it comes out of this exponential version of the equation, and therefore the reaction rate increases. And so here ends up being the equations that we end up using to solve lots of problems. So you can calculate an activation energy from the Arrhenius equation. We could take this and turn it into a straight line form, and you see if you plot the natural log of K versus 1 over T, you get a slope equal to the negative activation energy over R. Remember units again, I'll stress. Usually we write R in terms of joules per K dot mole. I want to warn you a little bit about this, though. Sometimes textbooks will have a multiplier for these inverse terms. So keep an eye on that. I'm going to give you a problem where I want you to make sure that you take into account, for example, often a textbook will, let's say, take the inverse temperature and then multiply it by 1,000, and then that's what's inserted into Excel. And then you have to account for that when you're calculating your slope. So I'll let you work on that. If you have data for rate constants at two different temperatures, you could use what I call this two-point Arrhenius equation. So I say these equations are somewhat deceptive. Maybe that's not the best word. They're not incredibly complex, but they have much basis for the work in the field of chemistry. A complete understanding of the rate constant of a reaction requires accurate calculation of both A and EA. Knowing the details of the mechanism and energetics means that you know a reaction. Lots of Nobel Prizes in the last 50 to 100 years were given with people who studied the kinetics of reactions and explained why they got the values they did. Here's a sample problem that I did. If you have access to Excel, please let me know if you don't. I just found some data in a different textbook and plotted it. So notice here I was kind of lazy. I only plotted 4 temperature points. I got the inverse. These are the rate constants in the natural log of K. So if you do that and you look at your straight line, you could get the slope and the y-intercept, and then I did the math for you here. So that's a problem that you could do on your own and see how I got it. I think I got it correct. Let me know if I didn't. The last thing I want to talk about is something that involves what's called reaction dynamics. One of my favorite classes in graduate school was a kinetics class where we spent a good deal of time on pictures like this. Let me try to explain what these pictures look like, or what the pictures, what's the information in the pictures, and just to round out your understanding of this. This is a very short section in our text. So I said to have a really detailed understanding of activation energy, and I said that is what's going on at the atomic level that contributes to the numeric value that you would calculate using the Arrhenius equation. you really need to understand something that we call a potential energy surface and their close cousin contour diagrams. So I like that Shane chose the easiest contour diagram possible to explain this. And I think if you have any questions on Monday, you could ask me what you're seeing here. So one of the simplest, probably the simplest reaction that you can think of is the exchange of a hydrogen atom with one of the hydrogen atoms in a hydrogen molecule. So it doesn't look really exciting, but you have a hydrogen atom colliding with a hydrogen molecule and then popping out one of those hydrogens and forming a new bond. So even for a ridiculously simple system as this, we need a four-dimensional plot, which describes 3 bond lengths, or 2 bond lengths and a bond angle, versus energy. You can greatly simplify the problem by removing a dimension by assuming that the minimum energy configuration is linear, so that only 2 bond lengths need to be specified. What that means is that this picture is easier to draw if you assume that hydrogen A is flying along and it hits BC right on the end, and all in that they form a line in the activated complex, and then you bang out hydrogen C pops off the other side. It's a much more complicated problem if you come in at an angle. But anyway, let's just assume that this is what we have. This collision between hydrogen A and the molecule hydrogen BC. In the diagrams below, the value of the distance of RA and the distance, that's what R means, of between BC are the separations between the atoms. Although the reaction could possibly take an infinite number of paths, the arrowed line is the one that takes the minimum amount of energy to traverse. The system travels along the path first through the valley on the left and then over a saddle point, which is the location of the activated complex, and then down through the second valley. Let me try to explain what I mean. If you look over here on the left, following that red line essentially is saying that notice the BC axis is unchanged. If you're following along here, essentially this is mapping how hydrogen A above is getting closer and closer and closer and closer to the BC molecule till it finally gets to a point where it hits. And essentially that's what's going on here. Once it hits, you create this activated complex. See how it slides up a little bit? Notice that the BC length has gotten a little longer. In fact, just at the saddle point, it's the same length as the HAB bond length. So this thing here, this activated complex, that's the state of our system right at that black dot in the middle. Once the collision occurs, then hydrogen C basically flies out of the valley. Notice that the distance RBC just gets longer and longer and longer, but the distance of AB is basically the same. You've created an AB molecule. Yeah, something that may be tough to see on here is that what I mean by this is a saddle point. This is a high point along this red line, and this activated complex is right here. That's what this contour diagram is trying to show you, that these are valleys at the end, and that you have to climb up. If you've ever been hiking or elevation maps, you're climbing up elevation to get over at the top, and then you slide down the valley. Actually, the way I drew this was the opposite. So I say here that figure A shows the potential energy profile for the H plus H2 reaction. Basically, the energy of the here, that's where hydrogen B is connected to hydrogen C, and hydrogen A is separated. Then the middle point is the activated complex where they're all connected and aligned. That's the most unstable point. And then the valley on the other side is when I've created a new molecule, HA and HB, and now HC is off to the side. And these two states are going to have the same energy because these are all the same atoms. I said much computer effort has gone into the calculation of the activation energy for this hydrogen reaction. I found out somewhere that the accurate calculation of EA in 1992 took 80 days of computer time. The close correspondence between the calculated and measured values of EA lends support to the validity of a linear activated complex. So basically, by doing this calculation and calculating a picture that looks like this, they essentially proved that when this reaction occurs, it really happens the way that we mapped it out earlier. So even though the mapping this out was sort of for simplicity, in drawing the pictures, it actually ends up being the real mechanism. In other words, HA coming in at an angle to this would not lead to a reaction. Would not lead to a reaction. So my mess of scratches here hopefully allows you to understand this. If you want to take a look at the book more carefully, please be ready with any questions on Monday. All right, I found some problems from the end of the chapter that you could work on for Monday. I will work on them myself. I haven't done them yet, but they look doable. Let's see. I guess the page isn't important. They're just the end of the chapter questions. It looks like 734 and 735. And then also problem number 70 is on 741. So these are the 5 problems I'd like you to work on. I'd like you to work on 26, 29, 30, 34, in the first half of number 70. A couple of these will require you to bust out your old Excel, and you could look at the problem that I already did for you. On the earlier problem set, there was 27, 32, and 33 involve the Arrhenius equation. So if you could work on these before I see you Monday, that would be great. I know we're not going really fast, but just to give you something to do, and if you want to hit me up with a question before Monday by email, I can get back to you. But if you don't hear from me again, we'll meet Monday at 11:30 Eastern. I may post another video just if you want to go ahead. I'm not going to sign any problems from that, but I think maybe Sunday I'll use some of my time in that way. All right, everybody. Hope you're doing well, and I'll see you on Monday.